Okay, I'm sick with a nasty cold, and sick of the sickness of the world in general, as anyone who pays attention is. So I'm going to try to distract myself by contemplating and summarizing Archimedes' proof of the quadrature of the parabola from around 250 BC. Why? Because Archimedes makes sense, and in times of widespread madness and irrationality it seems auspicious to return to the imperishable wisdom of those who came before, ideally as far back as you can go, if only for the immediate therapeutic benefit of listening to someone who makes some sense, basically. So, what is this? Proof of the quadrature of the parabola. What is quadrature? It's basically an old word for area, which I'm going to take for granted as being intuitive. It is essentially intuitive, considered in two dimensions, but just as a side note, the concept of area has a very complex history, and the more that it's generalized into what would be called hypervolume across infinitely many dimensions, up to and including fractal dimensions eventually, this concept gets stranger and less intuitive. One quick example of that would be considering the unit hypersphere and its hypervolume across infinitely many dimensions. It remains constant. One, basically. It's just, one in one dimension, one in two dimensions, one in three dimensions, and so on. But the hypervolume of a unit hyperpyramid, or hypercone, as the number of dimensions approaches infinity, this hypervolume shrinks to zero. In zero dimensions it doesn't exist, which is strange because the hypervolume of a sphere does exist in zero dimensions. It's essentially a point. In one dimension, it's the hypervolume of a unit hypercone or hyperpyramid is equivalent to that of the unit hypersphere, and then from there they shrink to zero, which is just not intuitive. So anyway, quadrature basically is referring to two-dimensional area in a nutshell. What is a parabola? It's a conic section, right? So if you take a three-dimensional cone and slice it in a certain way, basically if you slice a plane such that it slices the cone only in one spot of the cone, I guess, one area of the cone. In other words, it's not cutting two cones at once, it's just cutting one cone. You get a parabolic curve. We would understand it in modern terms as the function f of x equals x squared. Archimedes understood it as a conic section, though they didn't use Cartesian coordinate systems yet. They didn't think then in terms of exact measurement of lengths or coordinates and so forth, or functions. They thought predominantly in terms of ratios and proportions, meaning comparisons of two or more objects. So proof of the area of anything in Archimedes' time meant proving that the area of the thing in consideration is equivalent to something else that's known. Okay, so I'm going to summarize Archimedes' argument in the way that makes the clearest sense to me, without, I think, compromising any of the essential logic of the argument. But I'm going to use a few modern conventions to make it clear, at least for myself, and I assume others. Because Archimedes' argument, it should be said, is brilliant and fascinating and worth reading, but very confusing from a modern perspective. Especially the first proof. He offers two proofs, in fact, of the quadrature of the parabola. And the first proof is a mechanical proof that is very interesting, but it's very confusing at first, at least. Anyway, I'm trying to make it as simple as possible here. So we're first going to consider, I should say that the area of the parabola is referring to the area encompassed above the parabolic curve and the area below the parabolic curve, the integral, as we would say now. So this is essentially Archimedes close to 2,300 years ago, discovering what would now be called integral calculus. He didn't generalize the results. That didn't happen until Cavalieri's quadrature formula. Basically, the formula that everyone is taught in modern calculus. The power rule formula for integrals. But we begin by considering a parabolic segment. So a section of the parabolic curve cut with a line. I'm considering a symmetrical example first, but this is generalized. This proof applies to any parabolic segment, asymmetrical and symmetrical alike. I think it's just easier to start with something symmetrical. So we're considering this section of the parabolic curve contained within this rectangle. And we're first going to look at these two lines and establish the ratio between these two lines as our foundational concept. So we're connecting the midpoint of the line that is connecting the boundary points of the parabolic segment to the vertex of the parabola along the axis of symmetry, this line AB. We're then going to construct this line CD by taking the midpoint between point B and the boundary point here, and the point along the parabolic curve that's immediately below point C, i.e. CD is parallel to BA. Or I should say CD is parallel to AB, whatever. Anyway. What is this point along the parabolic curve? Right? Well, in a Cartesian coordinate system, point A would be the origin 0, 0. Point C would be the point 1/2, 1, considering that this is a unit length. A to the edge of the segment, in other words. So this point D would, in a Cartesian context, have the coordinates 1/2 and 1/4. 1/2 squared is 1/4. So the length of the line segment CD is 3/4. 1 minus 1/4. This is 3/4. This is a unit length, the line segment AB. So the ratio between these two lines, importantly, is 4/3. So CD times 4/3 gives us AB. Okay. Now let's consider a unit length, AC, and similarly go to the midpoint between the point C and F and construct a line segment of 3/4 length. So the ratio between AC and ED is the same as AB and CD above. And then let's construct first a right triangle connecting this unit length CF and the unit length AC, and then construct an outer triangle that encompasses the hypotenuse of that right triangle and these two outer lengths. The key here is that the line that would be parallel to the hypotenuse of this right triangle going through point E would contain these two outer triangles. The key ratio to consider is that this outer triangle AEF, according to the logic that we established here above, the area of this outer triangle is 1/4 that of the triangle ACF. How do we know that? Well, if we, as I point out here, I believe, if we take the overall area of this construction and subtract the area of AFC, we're left with, a simple subtraction here. The overall area of 5/8 minus the area of the right triangle 1/2 gives us 1/8. 1/8 is 1/4 of 1/2. Okay. Now we are going to take both of these concepts back to the parabolic segment, and we're going to construct an inscribed triangle. The 3 points of this triangle will be the 2 boundary points of the parabolic segment, and a vertex that is along the parabolic segment and has a tangent line that is parallel to the chord connecting the 2 boundary points. When I try to explain this proof to folks, it seems like that is the most confusing idea. But once you see what that means, it's quite clear. In a symmetrical example, the tangent line to this vertex point that's parallel to the chord above the base, you might say, of both the triangle and the parabolic segment, that tangent line is, equivalent to what would be the x-axis in a Cartesian coordinate system. But again, we can generalize this situation to an asymmetrical segment, an asymmetrical triangle. And as long as the vertex of that triangle is along the parabolic curve and at a point where the tangent line to that point is parallel to this chord, that is the associated triangle in this proof. That's the key reference point here. So we construct then this same outer triangle above on both sides of this new inscribed triangle, and we can iterate that process infinitely. That's what Archimedes is most famous for, probably, is the method of exhaustion, which means iterating a process infinitely in theory. That is, you might say, the core concept of calculus that he was the first on record, anyway, to have a fundamental insight into. So if we add the areas up of these triangles that we are constructing, we get a geometric series, an infinite geometric series, which converges to 4/3. Archimedes demonstrated that with a square here, so he's saying if we add up the area of the unit square, 1 plus 1/4 plus 1/16 plus 1/64, and so on infinitely, that area converges to 4/3. I won't bother proving that in itself, right? But the conclusion that we draw from this is that the area of the parabolic segment is 4/3 the area of this original inscribed triangle. So, in a unit length scenario here, if the length of this base line is 1, then we have, is 2. Then we have an area of 1. These 2 outer triangles have together an area of 1/4, and so on. Okay, so we have proven the area above the parabolic curve. With that, we can then prove the area below the curve by using subtraction, essentially. So, just as we did above here, we can take the overall area of the rectangle that contains the parabolic segment and the inscribed triangle within that segment, knowing that the area of the parabolic segment, meaning the area above that curve, is 4/3 that of the area of the inscribed triangle. We can subtract that from the overall area of the rectangle and divide it by 2 to isolate this one section, and we'll get 1/3. If we generalize what we're doing there algebraically, and of course Archimedes did not use algebra, he didn't use variables, that came later in the history of mathematics, but we can just describe algebraically what we're doing there and simplify the terms to get what is in fact the integral, the indefinite integral formula that, evaluated between any 2 points along this curve, will yield the area of the area under the parabolic curve. And there you have it, basically. Archimedes is discovering integral calculus. We can then, with modern notation, express the same process, basically all of this, much more directly, much more efficiently, by saying this line above, that's the base of the parabolic segment, we can represent as a constant function, a flat line, 1. We're considering it between these two boundary points, or limits of integration, -1 and 1. And we're looking under that curve and above the parabolic curve from between the same boundary points, and that will give us the same result as above, 4/3. And there you have it. There's one more thing I was looking to comment on that is related, and I think interesting. Let me see here. And it pertains to Archimedes' measure of a circle, which also involves the method of exhaustion. It's around the same time. Archimedes' main hits were the measure of a circle, the measure of a cylinder and a sphere, and the proof of the quadrature of the parabola. So Archimedes proves the area and circumference of a circle using the method of exhaustion. I won't bother going into that, but the result is that he ends up comparing, again, as a ratio, because that is the standard way that he and all ancient mathematicians of his era approached proofs in general. The point was to arrive at a comparison, a ratio, a proportion between two objects that are equivalent. So his measure of a circle amounts not to the formulas that we would use for measuring a circle in isolation. It amounts, in his mind, to a comparison between a circle and a right triangle that have equivalent area. Now, once you understand that, you can understand this transformation of the circle into that triangle very interestingly. So if you imagine that you cut the triangle along a radius and then unfold it or unwrap it in one continuous motion, you can directly transform this circle into this triangle, which is interesting in itself. But there was an article from 2001, Mechanical Derivation of the Area of the Sphere, by these mathematicians here, who were considering this 12th century Rabbi Abraham Bar Hia, who probably didn't have access to Archimedes' writings, and thus, as far as he knew, was pursuing original results. He calculated the same result in essentially the same way, except with a symmetrical construction. So rather than unwrapping the circle clockwise to the right, like I've done here, and ending with an asymmetrical right triangle, he unwraps the circle from the center out to either edge, or to either side, and arrives at a symmetrical isosceles triangle of the same area. Pretty cool, but more interestingly, the mathematicians above realized that you could use that to calculate both the surface area and the volume of the sphere in the same way. In other words, if you unwrap a three-dimensional sphere and flatten it, you get two cosine segments, and calculating the area of that shape will give you the same result as Archimedes, the famous surface area of a sphere. And if you project from that base a cone of the, what is it, the height of the sphere, I believe, you get the same result as Archimedes. Again, the volume of the sphere. What's really interesting to me is that this transformation above, Archimedes' transformation, doesn't work in 3 dimensions for the sphere. It works in 3 dimensions for a cylinder. In other words, you could take a cylinder and unwrap it in the same manner and arrive at a triangular ramp which will have the same volume as the original cylinder. You cannot do that, though, for a sphere. You will end up with a half cone that has larger volume than the original sphere. It's clear that that's due to the asymmetry of this transformation as opposed to the symmetry of the Rabbi Abraham Bar Hia transformation. But I just find that interesting. I wish I could ask Archimedes for his thoughts on that. It's interesting how this asymmetry works in 2 dimensions. It works in 3 dimensions for a solid of projection, but it fails for a solid of revolution, essentially. And therefore, this other interpretation, due to its symmetry, is also a proof of the surface area and volume of a sphere. Just kind of interesting. That's it.